Okay, well, there's no point in me going over what I'm going to say because you've all been told exactly what I'm going to say. But before I do anything else, I feel the need to make sure that you all will understand the terminology that I'm going to be using. Because if I start talking about iron and you think it's the wrong stuff, then it won't work very well. So right up until the 1850s, the only iron alloys that they were used in any quantity was pig iron or cast iron, which came out of a blast furnace. And then you had the malleable bar or wrought iron, all the same stuff, but generally referring to different sizes. So malleable was the general term, bar was for the the heavy bar that was a sort of merchant bar sold, and wrought iron was when it was sort of made into little things. And the conversion from pig iron to malleable iron was carried out in a finery or a forge, and the 4% carbon that was present in pig iron was removed to virtually zero. Cast iron, well, I don't need to tell you a lot. This cast iron was almost entirely restricted to compression. It did have some tensile strength, but of course it had very low fatigue resistance and very low impact strength in tension. So if you wanted to use something in tension, then you use malleable iron. Steel, I'm not going to talk about steel today, just to say that in those days, steel was effectively what we now call tool steel, which was 0.5 to 1.5% of carbon and just used for cutting tools. Now, they say, tell them what you're going to talk about it, and then tell them what you've told them. This is the graph of bar iron production from 1700 to 1825, and it's split into two. There's British production, which is the blue line, and there's imports, which are mostly from Sweden and Russia, which are the orange, it's the orange line. And you can see that right from the beginning of the 18th century, about 50% of what was used in this country was actually imported. And there's a very good reason for that, because British iron, for the most part, was actually not very good. The problem was it was high in phosphorus. There were some ores which were not high in phosphorus, but they were in small quantities, and they tended to be used to augment the poor quality ores that were used elsewhere. So that was the situation in 1700, where everything, whether it was in the blast furnace or in the finery forge, used charcoal as a fuel. There had been experiments with using coke in the blast furnace. Some of them had worked technically, but it had never been turned into a straight commercial proposition until in 1709. That was when Abraham Darby was credited with actually first producing pig iron in the blast furnace. He didn't, but he did make a go of it. He did make a commercial go of it. But for 50 years or so, this pig iron could not be used to make bar iron. And that was because it contained sulfur. Sulfur made the iron very difficult to work down at high temperatures. It was what made it they called it hot short. So sulfur made things hot short. Phosphorus, which I mentioned earlier, made things cold short. That meant that you couldn't actually work them very easily or at low temperature. And then post 1766, sorry, let's go back to the 1750s. Although they could actually use the iron that came from the blast furnace to convert into malleable iron, they couldn't do it with coal or coke. They still had to use charcoal to make that transition. And then in the 1760s, they first began to use coke and coal to make that transition. And that's what I'm going to talk about tonight. So we're going to start with cast iron, okay? Now, since we're starting right at the beginning of the 18th century, This is a very good place to start because it was an advertisement in the London Postman in January of 1700. And it just shows you the sort of things that they were already making in the foundries of those days. This foundry was actually in Blackfriars in London. It didn't have a blast furnace. It was remelting scrap and probably pig iron from blast furnaces. But I mean, I'm not going to read them out, but you can look through that lot. You can see what's there. And it's a fairly interesting list, actually. Now, the metallurgy of cast iron is actually not at all simple. You actually need to have a different composition for every section size that you cast if you want to get the optimum strength. And this table was published in 1909 by an American called Forsyth, and it basically shows that if you want to make a thin casting, you have to have a lot of phosphorus and silicon. But if you want to make a thicker casting, then you reduce the amount of phosphorus and silicon you've got. I can't get excited about manganese and sulfur. It's all too complicated. So why? Well, there are actually two phenomena that were involved here in this particular science, if you like. First of all, with the very thin castings, you had to be careful to get the right kind of iron in the first place, because out of an 18th century blast furnace, you could get two completely different kinds of iron. And it all depends on how that 4% of carbon in the cast iron precipitated into the solid structure. If it precipitated as iron carbide, Fe3C, then it was known as a white iron. If it precipitated as graphite, then it was known as grey iron. And these two irons were so different, you can't really imagine that they were anything like the same sort of but you could actually get, you could take a specific composition of iron and you could cool it quickly and you would get white iron, and you could cool it slowly and you would get grey iron. So speed of cooling was an important part of the reason why you would get these two metals. But the other thing was chemical, and you needed, if you wanted to get grey iron, and everybody who wanted to make a casting wanted really grey iron, then you had to have a high silicon and phosphorus content, because that encouraged precipitation of graphite. So that was the first phenomenon. The second phenomenon is that if you cast a thick casting with a composition that was meant, as it were, for a thin casting, your graphite flakes would be very large. Now here you can just see I just happen to have these analyses in my collection. The right-hand one is from a 5mm casting. The left-hand one is from a 10mm casting, and you can see the graphite flakes in the 10mm casting are much thicker, much bigger than the 5mm. If you actually cast those into a 20mm casting, then the graphite flakes will be very large, and the graphite flakes are, of course, a pathway for the cracks to develop throughout the material. So to get the very strongest casting, you wanted to have an iron that was just grey, that had the smallest flakes that you could get. This was a classic thin casting. These are Dale Company pots. Nobody you ever heard of Dale Company before? Actually, the Dale Company was what the Coalbrook Dale Company was called in the 18th century. If you have cast into any pot you see Dale Co., then it was made in the 18th century. If it has CB Dale written on it, then it was made in the 19th century, just in case you wanted to collect pots. The main thing about these pots was this was the business that Abraham Darby created when he first used coke in the blast furnace, because the one thing that coke iron could do better than charcoal iron was make a thin casting. But it naturally produced a high phosphorus and a high, naturally produced a high silicon. You had to choose the ore to get the right high phosphorus. But basically a 2-inch, I think in old money, by the way, so it's a 2-inch casting here. the base plate of the iron bridge, 1779. The thickest castings that you could make were really cannon. Funny enough, there's very little analysis of cannon. There's probably more old cannon around than any other kind of casting, and they're all dated. But very, very few people have carried out any sort of analysis on them. And I'm dying to find a broken cannon dating from the Napoleonic Wars, but there we are. So let's test foresight against what they did in the 18th century. And if you compare the actual analyses of these pots, of these castings, two of which I've made myself, the third one was made by a Canadian called Unglich, you can see that's pretty close. And actually, silicon and phosphorus are sort of interchangeable. And if you compare the two added together, I mean, the first two are very, very close indeed. So I think you have to say that they pretty well knew what they were doing when it came to cast iron. What you will remember, I'm sure, structural chaps, Thomas Telford always used a gentleman called Hazeldine to make his castings. And he swore blind that Hazeldine made stronger castings than anybody else in the country. And most of the bridges and things that Hazeldine cast are still there. Okay, so I'm going to move off castings. So for the first 50 years, you couldn't make malleable iron with the pigs that came out of the coke-fired blast furnace. Why not? Well, it was because inevitably you had sulfur present in the iron that came from, that had been anywhere near a piece of coke or coal. You reduced the sulfur content of coal when you coked it, but you still had sulfur left. And if it came in contact with the iron would pick it up. But then suddenly in the 1750s, a whole plethora of new furnaces were built specifically to make iron for the forges. So what happened? Now, this is not an 18th century blast furnace. What you need to look at here, and I don't know whether you can actually see it, but the temperatures, can you see the temperatures that are here at the back? The way a blast furnace works, and I'm just being very, very simple here, is that you burn the carbon at the bottom, and at 1500 degrees centigrade, the stable form of the oxide form of carbon is carbon monoxide. So you produce a load of carbon monoxide at the bottom furnace, and as it goes up, of course, the furnace cools. It comes to a point, and it says here 700 degrees centigrade, where carbon dioxide becomes the stable form. And at that point, carbon monoxide can reduce iron oxide to iron. And that's where, in the solid state, the all-important reaction happens. Now, there's a problem here. When you're using a fuel that is less reactive, you get a steeper temperature gradient in your blast furnace. And that means that basically you get more heat lost out of the top of the furnace because the gases leaving the furnace are hotter. Coke is a very variable material. It's inevitably denser and less reactive than charcoal. So when you put coke into a very early 18th century blast furnace, height about 20 feet, you had to make sure that you had a very reactive form of coke. And sometimes in the 17th century, people succeeded in making iron in the blast furnace with coke, and sometimes they failed. And when they failed, it was because they were using a coke that was not reactive enough. And what it was doing was effectively pushing this temperature of 700 degrees out of the top of the furnace. What that meant was also that even if you had a reactive coke, you had to be very careful to make sure that you didn't push the temperature of the hearth too high, because you would do the same thing. So if you had too hot a hearth, you would again push the reduction zone out of the top of the furnace, which meant that you were limited in how hot you could have your hearth. Now, actually, you will read lots and lots of reports that have been made, well, prior to me coming along, actually, sorry, where they would tell you that the coke-fired blast furnace was hotter than the charcoal one. It wasn't, not in the hearth anyway. In fact, it had to keep the hearth quite low in temperature, simply to make sure that it got the reduction zone in the right place. But this is a little bit just to prove the point. This is the coal coke that they used in the Coalbrookdale furnace, the Dale Company furnace, was nearly as light as wood coal. Now, what did they do then to get the to be able to get the iron into the forges by 1750? Well, what they did was built their furnaces bigger, higher in particular. But they couldn't do that in most cases without consuming an awful lot more water, because a bigger furnace required more air and therefore required more water to drive the bellows, because they were all driven by water wheels at that time. So the thermal efficiency of a blast furnace is basically set by the height of the blast furnace. The output of a blast furnace is set by the volume inside the blast furnace. So we can be reasonably sure that if they improve the output of their blast furnaces, then they were also making the furnaces bigger. And the only way they could easily make them bigger was to make them taller. So we know what the output of the Coalbrookdale furnaces were. There were two. They started off at about 4 tons a week. They sort of crept up to 5 tons a week over a sort of 20-year period. But then Richard Ford, who ran the company as an interregnum between Abraham I and Abraham II, introduced the idea of a horse gin. And this was simply a horse-driven pump to pump water back from below the blast furnace up to the pool at the top of the hill. And at that point, the peak outputs went up from 5 tons to 9 tons. And then, as a natural follow-up, they installed a Newcomen engine to do the same job. And at that point, they got 12 tons at the peak. So clearly, they were increasing the size of the furnace, and therefore, almost certainly, being able to increase temperature at the bottom of the furnace. Now, all of these furnaces in Shropshire, there was several in Shropshire and there was a couple in South Wales, but all the ones in Shropshire used the Newcomen engine to do what to pump the water back up into the pool. Actually, the Newcomen engine was a jolly big, sorry, something making a noise. Oh, it's killing flies, I think. The Newcomen engine was actually a big marketplace for the Coalbrookdale company, because they cast almost all the bits for it in the early days of the Newcomen engine. And I love this picture. It shows a cylinder being taken out. This was actually in 1758. But the last talk I gave here was about a chap by the name of John Baildon, who basically took the British 18th century iron technology to Silesia in Poland. And he took a cylinder from Broseley, it was from a firm called Banks, to Silesia. And I presume there were loads and loads of horses along the way, but of course it must have gone most of the way by sea. Okay, so how was it that simply increasing the hearth temperature of the blast furnace was able to remove sulfur? And it was all down to the amount of lime that you could use in the slag. They'd always added lime as a flux to even charcoal blast furnaces, because it increased, it decreased the amount of iron that you lost in the slag. But the problem with using a higher amount of lime is that the slag has a higher melting point as a result, a higher fluidity point, I think is probably the best way of putting it. In order to remove sulfur, you had to have a higher basicity in the slag, which required a higher temperature to melt it crudely. These figures here are from a gentleman called Tilecote, and you see that in the 18th century, the charcoal furnace at Charlecote ran a basicity of slag of 0.4, whereas Dale Abbey, which was on coke, ran a basicity was nearer 1. The basicity, as you'll see here, is calcium plus magnesium over silica. Just to emphasize the point, these are basicities reported by a chap called Pavlov, who was a Russian, and he reported all the slag basicities that were used in both the charcoal furnaces and the coke furnaces that were run in Russia in the sort of middle 19th century. And you can see here that the coke furnaces had a basicity of over 1.5 on average, whereas the charcoal furnaces got away with 0.6, 0.7. So the important thing about raising the temperature of the blast furnaces was to be able to raise the basicity to be able to remove the sulfur. Now, I have to say that what I've just told you there is, it's not speculation, it's a lot more than that, but there's nobody has ever actually satisfactorily shown that this is the case. The only evidence to support what has to be the case is this, which was the specification for a lease that demanded the supply of 300 tons of pig iron a year, which had to be made with a proper mixture of lime and limestone, mine and limestone, to make it fit for making bar iron. Nobody else has satisfactorily explained any other reason why Abraham Darby II was suddenly able to build those blast furnaces in Shropshire. Right, so we now move on to actually making bar iron. And in order to do this, you have to remove, first of all, the silicon, because you can't remove the carbon until you've removed the silicon, because you're oxidizing the carbon out. The silicon is actually much more reactive, so the silicon gets oxidized out first. Then you remove the carbon. In oxidizing the silicon and the carbon, you oxidize a lot of other impurities in the iron as well, and they will all sort of go into the slag. So the next thing you do is try and squeeze the slag out. And so you hammer it, you basically treat it as a sponge. You heat it up to well above red heat and beat the slag out of it. The result is this. And here you can see that you get a terrific amount of slag left in your wrought iron. You've got two specimens here, one of which was from the end of the 16th century in mid Wales. That blast furnace that only worked between 1590 and 1599, something like that. The other one is a puddle, probably a puddle beam, a puddled piece. And what I've illustrated here is that the slag stretches out in the direction in which you work it. And you want that slag to be as well mixed and as well as reduced as much as possible in the first place. But it wasn't just slag that gave you this heterogeneity in bar iron, because you got a terrific variation in the carbon content. And this is a section, it's actually a composite map of a bar iron that was found in the off the coast of Holland. And you can see that dark area on the left. That is high carbon. In fact, the top picture is from that dark area and shows that that's almost entirely perlite, which has got a carbon content under normal circumstances of 0.8, but I suspect that given the presence of other impurities, that's probably a bit less than that. Whereas the light side has got virtually no carbon in it at all. It's all ferrite. So one of the things that I'm going to do in my research is really try and explain how this happened within the fining furnace. I think the basic thing is quite clear. You have different conditions within the fining furnace, which gives you the different result. But it's probably a little bit more complex than that. Anyway, you don't only get a heterogeneity in the carbon content, you've got the heterogeneity in the slag, and this is a silicon map. Both this is a silicon map that's been taken off a micro XRF machine, and you can see that the different lightnesses are where there's different amounts of silicon, and that's a reflection of the different slag. Okay, so this was the sort of stuff that you were getting out of those the fineries. But then they weren't actually doing awfully well, because all they could make was nails with the iron that they produced. And this was true of 1784, when Richard Reynolds, who was brother-in-law of Abraham Darby II, wrote to Lord Gower, who was president of the Board of Trade, I think, at the time. He said, we can make nails with our coke iron, but we can't make anything else. We can't make a decent bar from it. And the reason for this was this phosphorus, as I talked about. British ores had lots of phosphorus in them, and that made the iron cold short. It gave them a certain amount of hardness and a certain amount of rigidity, which was fine for making nails and for things that really didn't matter in terms of their mechanical properties. But if you wanted something that was going to be tough and was going to be used for things like chains and the like, then you're going to have to get rid of the phosphorus. There was this question of being able to use the coke iron, actually, the processes had to change when coke iron came onto the market as opposed to charcoal iron, pig iron, because of the silicon content that you had in the iron that came from a coke-fired blast furnace. When they had iron from charcoal-fired blast furnace, they could get away with what was called the French or the Walloon method for fining the pig. But if they had grey iron with a high silicon content, they had to use what was known as the German process or the French Comte process. And the thing about that was that actually in the latter case, you had to use iron oxide additions to help reduce the, remove the carbon. Whoops, that was quick. What's happened there? Okay, yeah. So this is the question then, up until 1760, 1770, I had to use charcoal to make the transition, but they developed a method first of all, in the 1760s, the Wood brothers developed a process which was known as potting and stamping, but that wasn't very successful, and it was rapidly overtaken in the 1770s by the Wright-Jessen process. And what they did here was get rid of the silicon first by putting it in what was known as a refining furnace or a running out fire. And this was basically a pile of coke on which they put the pig iron, blasted it with air, and heated up to a point where it melted and ran out, as it were. They then took that iron and at red heat, it still had quite a high carbon content, still had other things in it, but they were able to bash it into a flat plate. but at that temperature. And in doing so, they opened up some grains, opened up wherever the sulfur was able to be removed, washed it in lye to get rid of any sulfur that was so revealed. And then they put these bits of iron broken up into crucibles, put a lid on, and they put them in a reverberatory furnace. Now, a reverberatory furnace was the general heating process that was used throughout the 18th century. If you wanted to heat anything up to a high temperature, whether you wanted to heat charcoal, whether you wanted to melt iron, whether you wanted to use heat for any purpose, annealing, whatever, you used a reverberatory furnace. And it's very simple. Basically, it was just a coke bed on the right, you can see there, with the normal sort of, provision of both primary and secondary air. The hot flames went over the roof of the reverberatory furnace and reflected downwards onto the bath or whatever was in there. And then the whole thing was driven by a chimney, which provided the drag. Now, you sometimes see it erroneously suggested that the reverberatory furnace ran on coke. It didn't. It ran on coal because you wanted a nice long flame and you wanted the gases, the volatiles to burn, over the charge. This is a bit of serendipitous discovery. Somebody at the Ironbridge Museum had found some bars of iron in the Severn at Broseley. And so I put these on the XRF phosphorus map. Yes, produced the phosphorus map, and got this structure. Now, this is a solid piece of iron, but you can, what's interesting about this, you can clearly see the bits of iron that were put in the crucibles and were welded together. This is a solid piece of iron. You're not looking at iron with any sort of gaps between it. What you are looking at is areas where there is no phosphorus. Because when this was put in the crucibles in the solid state, the outside of the iron the phosphorus was removed from the outside of the iron, and that showed up when you put it under a phosphorus map when it was beaten into this shape. I found that was really fascinating. The stuff was still very heterogeneous because this is a silicon map, and you can see there's a variation in silicon content, actually very much mirroring the difference you got. So that last we can now move on to Henry Court, because the potting and stamping process was actually quite a success. It came effectively to take something like a half of the market producing bar iron by about the late 1780s. But it didn't produce an iron that was substantially better than the charcoal iron did. It was still overall high in phosphorus. But that wasn't the case with puddling. Henry Court, well, basically he showed that you didn't need the crucibles, that actually you wouldn't get sulfur in your iron, which is what the big fear was, that you could just simply rabble the iron around in the bottom of the reverberatory furnace. And very quickly, it was demonstrated that this was an amazing way of making bar iron, because it removed the phosphorus. And that's the key part of the puddling process, which is not always observed. Now, Henry Court, of course, I'm sure you know a bit about the history of Henry Court. He was a tragic figure, basically. Things did not work out well for him. James Watt said that he showed ignorance of the common operations of making iron, which is not really surprising because he had never made iron before, before an uncle of his wife left her a forge down near Portsmouth. Now, Portsmouth was not the main iron-making area of the country at the time, but he inherited this forge. And Sir John Dalrymple remarked that he was ingenious, but ingenuous. Joseph Black, who was the proposer of the concept of specific heat up in the Scottish Enlightenment, said that he was a plain Englishman without science, which is probably true. In his patent, he said, "The whole of my method may be completed without the necessity of using the finery, the charcoal, the cokes, the chauffery or hollow fire, and without requiring any blast by bellows or cylinders." So the running out fire that you saw before was not required, says he in his patent. The problem was he was using the wrong kind of iron. He was using the pig iron that came from the ships of the Royal Navy that were being broken up and had been made a long time previously in charcoal blast furnaces. And it was white iron. And white iron worked a treat. Why did it work a treat? Well, I'm sure you all know the iron-carbon phase equilibrium diagram. It's the most important technological diagram there has ever been in terms of meaning. The problem with grey iron was that it's here. And when it melts, it produces a liquid, just about a pure liquid. Whereas if you melt white iron, you take it up into this area where you've got a mixture of solid and liquid. It's pasty. And when it's pasty, you can stir it around very easily. When it's liquid, it's not so easy. When they tried to do what Henry Court did in Portsmouth, in the areas where they had coke-fired iron, it was very difficult to make it work. So what did they do? They reverted to the running out fire. And they turned the iron from a grey iron to a white iron in just the same way that that Wright and Jessen had converted their iron into suitable charge for their crucibles. And actually, that wasn't the only use of the running out fire, because it had also been used in that interregnum I spoke of, where they wanted to use, where they still had to use charcoal, but if they used the running out fire before they put it in the charcoal finery, then they could actually make significant economies. Anyway, let's move on. This iron that he produced in Portsmouth was first of all tested by the Navy and was found to be every bit as good as the best Swedish bar iron. Very low in phosphorus. And this is, I don't know whether you can read this, but this was the James Hutton, a father of geology, another member of the Scottish Enlightenment. And he said, what most amazed us was the curing of the cold short, removing phosphorus. The Navy ran a sort of special test comparing an anchor made with Swedish iron against one of Henry Court's, one made with Henry Court's iron. And the Henry Court's product actually came out better than Swedish on something like 60% of the occasions. I think they ran 5 tests. So, you know, clearly it was very good, but it had technical problems to begin with. But then there's another fascinating part of this, because it's not immediately obvious how the puzzling process removed phosphorus. Now, you know, people know about the chemistry of phosphorus. If you oxidize it and you run it at a low temperature, then you can get a distribution between the matrix and slag, or between the iron and the slag, which improves as you lower the temperature. But when Henry Cort demonstrated this to William Reynolds, who was the son of Richard Reynolds that we mentioned before, Abraham Darby II's grandson, he said that Henry Cort could actually make the iron tough or cold short just by changing the process. And what I'm hoping to do is discover how it was that he did that, because it's not immediately obvious. Just to demonstrate how this sort of worked in the two-stage process, these figures are from Isaac Lothian Bell, who produced a very important book in the 1880s. And he was one of the first sort of thermochemists dealing with the iron industry in Britain. So this shows how you reduce the carbon and the silicon and the sulfur and the phosphorus when you turned it from the pig iron into the refined iron by using the running out fire, the refining surface, and then how huddling it then sort of took that whole thing a stage further. So you've really got a very I'm just looking at the time to make sure I don't overrun. It just demonstrates really how the whole thing worked. Now I think going to run out of time unless I skip through the next few slides. The next few slides are actually to show that somebody else basically ran the puddling process before. In fact, there were a pair of brothers called the drainages. And it was just practiced in Coalbrookdale, never anywhere else. But it never came to anything. It was still being used alongside charcoal fining. Complete mystery as to why it didn't go any further. Well, part of the issue, perhaps, was this question of profile rolling, because Henry Cort, the year before he patented puddling process, patented the use of profile rolls to compress iron rather than just hammering it. And the whole idea was that, sorry, those are the profile rolls. Basically, you just had a series of rolls with the reducing profiles in them, and you put the malleable iron, the bar iron in one end and ran it through, and you could run it through till you got a decent piece of merchant bar that you could then sell, or you could run it right the way through and turn it into some other section. Cort actually patented this process and used it because before he invented puddling, he was recycling wrought iron from the Navy, and he particularly was given a whole load of barrel hoops that were nice and long and were actually sort of, in some ways, quite difficult to recycle. To recycle wrought iron, very simple. You heated it up, having cleaned it, you heated it up, and then just beat it together. And actually, if you made a decent piece of wrought iron from a whole mixture of scrap, it could be very, very good because you were getting it much more homogeneous than it started off as. Anyway, the thing is that profile rolls were very expensive. They were hugely complicated. They were very substantial. They actually had to be driven by 2 water wheels. So you had a whole load of civil engineering to go alongside the mechanical engineering. So basically, their use was only economic when you had a lot of stuff to put through them. Expensive. I mean, if you put a rolling mill like this in a charcoal finery, you'd probably you probably reduce the iron, the output for a week down in about 5 minutes. The antecedents of profile rolling, of which there were plenty, they used flat rolling and rolling for making rods, particularly for the nail trade, actually. In about 1590, there was a patent on profile rolling by a gentleman called John Payne in 1728, but nothing really became of that, which fits in with what Christopher Polhem. Now, I don't know whether you've heard about Christopher Polhem, but he was actually a very celebrated Swedish engineer. And he proposed the use of profile rolls quite early on in his life, but he didn't do anything about it himself. And right at the end of his life, in 1751, he bemoaned the fact that nobody had taken up his idea. But then an Englishman called John Purnell in 1768 started to use profile rolls for making bolts and rods, particularly in copper. And then suddenly that took off in 1783, which was the same date as the patent that Henry Cort had. And basically that was because there was a sudden demand for copper bolts from the Navy. They had decided that they were going to use lots of copper sheathing to protect the hulls of their boats from the various worms that they got out in the tropics. But the trouble was that the copper sheeting reacted with iron bolts. So they had to replace the iron bolts with copper bolts. And so suddenly there was a huge demand for copper bolts. And I think at that point, rolling became economic. That's John Payne's patent, which I won't bother with. This is the complicated drive mechanism, as I talked about. The thing was that a single puddling furnace was enormously productive, and you could possibly get enough iron out of a puddling furnace to justify rolling mills, but probably not. But on the other hand, you could have puddling furnaces staggering down your works, several in parallel, and under those circumstances, you could certainly justify a rolling mill. And really, I think Henry Cort's process took off and the Cranage one didn't, because rolling accompanied the use of the puddling furnace. And on the continent, they frequently referred to puddling as practiced as the Purnell-Cort process. Anyway, we come to the end because it's a nice point at which we can stop. You can see the result of this development. I mean, it's purely down to puddling and rolling that suddenly we were able to do with a lot less Swedish import. The Navy actually were very happy to use puddled iron instead of Swedish iron for its anchors and its chains. The imports continued because the Sheffield steelmakers didn't want, they weren't going to risk British puddled iron in their steelmaking. So they preferred to continue to buy in Swedish iron for its low phosphorus content. Now this finishes in 1825-ish. There was one more development, which I haven't really majored on because it wasn't 18th century. But they, it's not immediately obvious. I mean, various people have been cited as being responsible for the novelty. But I think it was one of those things that just sort of happened because people started using slag and iron oxide to protect the bottom of their furnace. And they discovered when they did this that they could actually, if you put enough in, and it was rich in iron oxide, then you could pour high silicon iron straight from the blast furnace into the puddling process. And the iron oxide would react with the carbon at the bottom of the bath, react with the silicon as well. And so they did then produce a single process for the puddling, which was known as either the wet process or the pig boiling process. And the interesting thing was that pig boiling and the dry process continued in parallel, being used right up to the 1780s, 1790s. And I can only surmise, and this is another thing that I wish to prove with my research, that the reason why was because the two-stage process, which was probably more expensive, was actually produced you a better iron. And I think it would have been lower in slag because you'd already removed the silicon. I think it was probably better at removing the phosphorus. Anyway, that's it. More or less finished on time, I think.
Okay, has anybody got a question? Julia, please.
Well, I just want to say the sort of basic thing, and you can tell me if I'm wrong. Surely the whole thing about the rolling mills and being able to roll profile bar iron like that arrived just in time for the railways. Because once you started having to roll 7,000 miles of wrought iron rail without the court process, correct me if I'm wrong, there wouldn't be a railway.
Well, yeah, there wouldn't have been rails in the quantities that we've had them anyway. And yes, the rolling mill was the perfect machine for making rails and lots of other things as well. But yeah, I mean, basically, it was a bit later than the rails really came into, a bit later than, yeah. There wouldn't have been. I mean, the whole thesis of this talk is without Henry Court, there wouldn't have been an industrial revolution in Britain.
Well, I think you could go. Because I mean, sorry. I mean, one of the reasons I thought would be interesting here is that none of us, all of us who've been obsessed with iron all our lives, none of us have a single solitary cluesy-woozy about what went into it.
Well, I hope that I've been clear enough to give you some idea.
Certainly speaking for myself, that's true. So this is all, well, I knew some of the terms and that's about it. I knew some of the diagrams, but it wasn't quite clear what each of them was doing. I have one question, and that is that presumably all these changes in the technology and the developments, the improvements they made in the iron were done entirely empirically.
Yes, yes. I mean, their knowledge of elements, for example, I mean, they certainly didn't know that phosphorus was responsible for cold shortness. They didn't know sulfur was responsible for hot shortness. They merely knew that if you did things in a certain way, then you got a better product or a better,
It just shows how they must have kept on trying to find a more economic way. Do you think it was driven by economics, or do you think this is a straight, well, there must be an element of straight curiosity, I think.
Well, economics must have played a very large part in it, of course. I mean, the important thing about the iron masters in the 18th century was that they were very keen on building up a business.
Yeah.
And they wanted to build up a business for a very particular purpose, which was to hand on to their sons and to provide a living for their offspring, which of course has long ago disappeared from British motivation for running companies. But I'm sure that's what they did, and they wanted to do things well, and they wanted to do things economically, and they were far from stupid. I mean, this whole question of how they knew how to make that cast iron suitable for for 5 millimeters or 50 millimeters. That can only have been done by experience.
Yeah, and presumably the understanding of elements and metallurgical composition, that only came about in the later 19th century. So until then, all the developments would have been largely empirical.
Yes, oh, absolutely, and particularly in Britain. I mean, the French were desperately trying to work out why things, how things worked, but they never actually made them work. Whereas the British tended to make things work and not know why.
No wonder the French would complain about English empiricism. So, Robert, you look as if you're brewing a question.
Well, I'm certainly brilliant. I'm still not entirely clear about how Court, working for the Navy in Portsmouth, came upon the idea of puddling.
Well, he first of all, he was recycling the scrap that the Navy wanted him to use. And that was just a simple matter of heating it up. Okay, putting it through rolls, but heating it up and rehammering it. But somehow they then gave him these pigs from the whole of their ships and said, you know, what can you do with these? So he must have popped them in this puddling furnace to heat them up and noticed that, you know, they started to melt and that he could stir them around. And I don't know, it must just be completely serendipitous, I think. Just he must have been a very enterprising chap. He desperately, you know, what did Dalrymple say of him? He was ingenious. I think he spent an enormous amount of money developing these things without any sort of thought of whether they were commercially possible or not. I mean, what I didn't say was that he had a business model that was completely different from anybody else really at that time, because having developed this process in, you know, far away from where the iron was made, he wasn't going to be able to make a mint of money out of it himself, so he had to license it to people. And that was why it was spread around, you know, and how they got to know about it in Scotland and in the Midlands, because he was desperately trying to sell licenses for people to use his technique.
Presumably also sorry, no, I forgot what my question was. Somebody else rescued me. Where was it? I was sort of ruminating. Oh yes, that's right. One of the problems with the whole technology is that it's not scalable. You can't make a sort of model blast furnace and produce a tiny little piece of iron and then scale it up 100 times and it still works. The whole thing is very much dependent upon doing it at the full size.
Mm-hmm.
And I suppose the one redeeming feature of that is if you're processing scrap iron anyway, then you've got a good feed of scrap iron from your failures.
Oh, yeah. Well, you always generated scrap iron anyway, because there was always a bit of iron that you had to cut off your castings. You had to have feeders and runners and risers and things. And then you had cast iron that was sort of left in the bottom of your ladles, which were known as sculls. And so you're always recycling, even in your, you know, your own stuff. But of course, there was loads and loads of scrap being produced, elsewhere. And that Blackfriars foundry that I talked about right at the beginning, I mean, they were sourcing cast iron scrap from London. Yeah. And, you know, they were right on the spot to do something with it.
No, many years ago, I had a metallurgical analysis made of some cast iron from an 1802 iron bridge, which had quite small sections, sort of inch square up to sort of 2 inches square. And the modern metallurgist was extremely complimentary about the Walker Brothers iron. I don't know, from Sheffield. I don't know where they bought it from, or if they made it themselves.
They made it themselves. Walker Brothers was very, very important.
One of the elements that he identified as being unusual was vanadium. And I can't remember what he said that affected in the iron. But certainly the iron was actually, could actually distort quite a bit before it broke. It was really quite, not ductile, but certainly wasn't really brittle.
Well, Walker Brothers made cannon, they made bridges. They must have known an awful lot about cast iron. The vanadium could only have come from the ore. There was no way that anybody could actually add vanadium to their iron. So they just happened to have it there.
Yes, so just serendipitous in that sense.
That was very, very interesting. Just one point, well, a couple of points. People do get the impression that cast iron has got no strength. If you actually start looking at the cast iron rails and so forth, you find that empirically, that cast iron rails and other things of this type were working on a tensile strength of 2 tons per square inch, which is quite low, but you can do something with it. Another point that occurred to me is that I don't think it really came over when you were talking about the court process, that the end product is a large steel ball, is a large ball about this size, which I've always taken was held together to a certain extent by the semi-molten slag inside, and that I'm not completely with you when you say you had to be on the cementite side of the diagram and away from the graphite. So that's one point. And the final thing is that removal of phosphorus. The great thing about the evolved form of the puddling furnace is that you've got this peculiar arrangement on top of the chimney that you can actually put a damper on it to change the oxidizing conditions inside. And I've always had the view that the way that they were getting rid of the phosphorus was to allow the iron to run into a more, on the furnace, and the furnace to run into a more oxidizing state. So you got a lot of iron oxide there, and that picked up the phosphorus, and it then was actually liquid enough to run out of the furnace. Now, up on Teesside, where I came from, what was happening there in the 1890s when they brought in the blast furnace, sorry, the Bessemer furnace, they were finding that although they'd introduced the basic Bessemer, it wasn't really working properly because they didn't have enough phosphorus in the cast iron that was in the molten iron that was going into the Bessemer converter. So what they were doing is that they're taking this high phosphorus slag from the wrought iron furnace and putting it into the top of the blast furnace to push up the phosphorus content. And in that way, they had enough phosphorus in the Bessemer furnace to provide the heat of reaction to keep everything molten.
Let's start with that last. You're thinking about silicon, not phosphorus.
No, I'm not. No, I'm not. I know what I'm talking about.
They had to have 1.5% silicon in the pig iron that went into the Bessemer furnace from the 1850s.
Sorry, if you look at the reactions in the base of Bessemer, you will find that phosphorus is providing a lot of heat.
Well, phosphorus doesn't have anything like the heat of combustion that silicon has. Anyway, let's park that there because other people can make their mind up about that. But let me go back to the very first thing that you said, which was when I talked about it being the iron being in the two-phase region of the phase diagram. What actually happened was that you started with it there, but as you removed both the silicon and the carbon, you effectively moved the whole thing to the left, so it became solid anyway. So you may have started with it being in a sort of semi-solid form, but it very quickly became properly solid. And then you had particles of iron suspended in your slag, as you said. And you pull this ball out, which was basically iron suspended in slag, and you squeeze the slag away from it.
That's right. That's right. So where does the graphite come in?
Well, the graphite would only come in if you were melting grey iron and you would get iron, you would get a liquid, a pure liquid instead of a semi-solid liquid. Now that actually took longer to melt because white iron melted quicker than grey iron. And then you would get a liquid, not a semi-solid. So you had to then basically oxidize it, both the silicon and the carbon, until you moved it into the two-phase area. And that took that time, and it took an extra energy. And that's why they opted to get rid of the silicon first.
Hmm. Okay.
We have a question from Justin Jackson in the Zoom audience. What was used for stirring the puddled iron?
Sorry, can you say it again?
What was used for stirring the puddled iron?
Oh, they used wrought iron bars, rabblers as they call them. They lost a bit in it perhaps, but basically it would stay solid at that temperature.
Questions? Does that film exist still? There was. They've got it now in Ironbridge. That rolling mill in Rochdale that closed down in 1960 something, and there's a film of it.
Yes.
Of actually seeing the iron going through the rollers with people jumping about with sort of red hot snakes at their feet.
Yes.
And I assume it must be somewhere because it would be wonderful to see it.
The rolls were actually installed at
Yeah.
the rolls and puddling furnaces were actually installed at Bliss Hill, and I've seen them in operation. And as you said, I have some slides of red hot iron zooming across the floor. Visitors were kept well away, and the people who worked on site, I think, had to wear heavy boots and jump very fast. Quite entertaining.
Now, Justine, did they actually run the puddling furnaces? Because they
They
have
must-
puddling furnaces there in the same
Yes,
building.
yes. Well, they must have produced red hot iron, and I think they were using puddling furnaces to heat the iron, but I don't think it was actually being puddled, because I think what they were using were the bars from the old Palm House at Kew Gardens. Which was good for all the time.
Yeah, yeah.
Sorry, just quickly, two reminiscences there. I witnessed the extrusion of the stainless steel bars for the Palm House restoration. And I and several other people were really quite cross. They didn't reuse the upper parts of the wrought iron bars, which were still entirely sound. And if you go to Bliss Hill, I think they still have demonstrations of the rolling. And they don't just wear heavy boots, they have incredibly heavy leather aprons which come right down to the tops of their boots. And this iron does whiz about. It really does. It's not a thing for an amateur to get involved in.
Well, just to explain about the balls and the wrought iron, when they come out of the furnace, they're about this size. You couldn't possibly put them in straight into a rolling mill.
No.
They've got to be hammered down into something of a kind of rectangular shape. And I have a personal interest in this because my great-grandfather was blinded in doing this particular process of hammering it down, and you got the bits of scale and slag, and he was blinded doing this. This would have been round about 1900.
Well, they certainly in the 18th century, they had to hammer the ball down using a proper big mechanical hammer to get it to the shape where it would actually fit in the rolls.
You couldn't possibly put a ball this size straight into a rolling.
No, it was hammered down first.
It
Sorry,
had to
was
be
that the
hammered
shingling
into
hammer?
That was the shingling hammer, yeah. But into the 19th century, they developed a squeeze mechanism for doing that. And that was a mechanical device that actually sort of, it just it was a bit like a nutcracker, I think, and it sort of squeezed the iron together.
And just a final point about how empirical things are. You can smell the sulfur in the iron and in the slag as it comes out of a blast furnace. So you would have some idea of how pure the material was from your nose. I don't know how you'd tell the phosphorus. You could tell the carbon to a certain extent by the sparks which are produced when the iron pours out of the blast furnace.
Yes, the interesting thing is, which I have to say I can't explain exactly, but in the 1730s, people like Emanuel Swedenborg talked about sulfur in iron. I'm not sure that they knew quite what it was, but they could smell it. And they actually said in Swedenborg, who was a Swede, a very good metallurgist, quite apart from the sort of Christian mystic that he became later. But he said the reason why the English cannot turn their coke iron into wrought iron is because of the sulfur. Now, I suspect that as far as they knew, sulfur was just a smell. I don't think they didn't know it was an element. Certainly, they may have thought it was a compound, but you know.
Sulfur was around it. Sulfur was around at that time. It was used for making gunpowder.
Indeed, it was. Yeah. I suppose they called it sulfur then. Yeah. But how they knew that was what made the smell in iron? I suppose, yeah, it's just literally done by the smell. Yeah. Smelled coke, smell of slag.
Can I shift the focus a bit? And one of the things that I understood when I first studied these things a long time ago was that the people developing the iron technology were quite remote from polite society. They were they weren't quite ignored. I mean, there were some people who understood what they were doing and the economic value of it, but they were not regarded as socially acceptable people. They were kept on the fringes. Is that unfair?
Well, I think there are probably two elements to that. I mean, one of them was to do with religion.
Yes.
I mean, you know, the Quakers. I'm sorry, I can't tell you the dates of when this all happened, but Quakers at the end of the 17th century were not allowed to take certain positions. They're not allowed to become professional. They couldn't get jobs within, as it were, the government, the civil service. They were sort of forced into alternative employment.
Yeah.
And that's when they went into industry.
Yeah.
And I'm not sure when that ceased, but it was probably towards the end of the 18th century.
Yeah. No, I wasn't entirely wrong.
No, it's
good.
That's one of the reasons that the Cadburys, that must be one of the reasons that the Cadburys and Fries, they all went to chocolate making. For exactly, they were all Quakers.
Yes, absolutely. And it wasn't only Quakers, any non-conformist.
Yeah.
Yes.
Yeah.
Okay, Rob's tapping his watch. Are there any more questions that we would like to ask? Okay. Thank you very much, Richard.